So what we're looking at here are some potential energy problems. We're going to look at potential energy due to gravity, a gravitational potential. You could use PE for potential energy if you like. I prefer using a capital U, as is often seen in textbooks. And for gravitational potential energy, we'll often put a little g next to it because that's gravity. Gravitational potential energy is equal to m times g times h, and this h here is really the important feature because it is some distance above or below or at some reference position, and that reference position needs to be asserted, it needs to be declared, or you just don't know how much energy you really have. Am I standing on the floor? Yes, but is that floor the 100th floor of a skyscraper? Thinking about potential energy and how much energy you have stored at that position is much different considering just to the floor versus you have somehow found your way outside the window and are now falling 100 stories down to the concrete below. So depending on what you've got going on there, you need a reference level in order to designate a potential energy. What we're going to look at here is this is a 9-C3 problem. What this problem is we have a wonderful room. I'll draw a little picture here because pictures are always worth more than the words themselves. We have a wonderful room and a lamp is suspended from a chain from the ceiling. Let's turn that lamp on. Boink. Wonderful. And this lamp is 0.75 meters down from the ceiling top. And the ceiling, or the room itself, has a height of 2.5 meters. What we'd like to do in this problem is we would like to figure out what is the gravitational potential energy, what is mgh, relative to a few different locations. We'd like to figure out what mgh is, gravitational potential energy, relative to the floor, relative to the ceiling, and then relative to the bottom of the chain where the lamp itself is. So if we do this, for our reference being the floor, we know gravitational potential energy is going to be mgh. In this setup here, our lamp has a mass of 2 kilograms. It's a very heavy lamp. It's like a chandelier. We know gravity. Gravity is going to be our 9.8 meters per second squared value. We're using positive values, unlike way back when we did projectile motion, because when we did projectile motion, we always just assumed down was the negative direction. But our direction is going to be dictated by the height here, or how far away we are from the reference position. In this case, our reference position is the floor. Our lamp is above it by some amount. So if this room has a height of 2.5 meters and this lamp is 0.75 down from the ceiling, well, 2.5 minus 0.75 gives us that distance there. And this distance is 1.75. And it's a positive 1.75 for our problem because we have this distance. We're above the reference level. So when we multiply all of that together, boom, 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 we get a value of approximately 34 joules. So there's 34 joules of energy stored at this position because a potential energy is an energy of position. The position itself has a potential, but when you place the object there, there's a potential energy. For part B here, we are looking at what is that potential energy of this lamp relative to the ceiling. So for part B, we're using the exact same equation, UG equals MGH. So there's our 2, there's the 9.8 from previously, we just bring those straight down. The thing that changes here is the height. In this case, our lamp is 0.75 meters away, but it is below the reference point. So we don't even have that energy yet. We're not even up at that point. We're beneath it. We're in a deficit, so to speak. So this is going to be 0.75 but it's going to be a negative 0.75 meters. When we multiply all of that together, we get a number of approximately negative 15 joules. Remember, joules being our unit of energy. For part C, we want to know what is this gravitational potential energy relative to right here, where the lamp actually is, the lower end of the chain. Well, same deal. M, G, oops, we're not bringing that down. We've got a new H. Our H here is 0. We are at the reference position. Because we're at the reference position, we're neither above nor below it. We're no distance away. It's just 0. And if we multiply all that together, whatever times 0 gives us 0. So if you're at the reference position, you have no potential energy. You're just there. But if you are above that reference position, you have a positive potential energy. And if you're below that reference position, you have a negative potential energy there. So that's kind of how we can approach these potential energy problems, gravitational potential energies, that is, with just MGH. So that wasn't too crazy of a problem. The big thing here is, what are you putting in for your H value? So pay attention to that, and you should be fine. With that, this problem's finished.